we are in crunch time a little bit. We only have 3 classes left after this, from what I am counting. So we need to talk about life still. I think we're going to do that on Tuesday next week. Then we'll do the Neptune-like planets, and then we will close this all down. So, questions, people, I've gotten a few emails, people running ideas by me for a final project. That's cool. Keep doing that. Send me ideas. Speaking of creativity, do something, submit something, gets your extra credit points. I really would love everybody in here to just get an A in this class. That would be really nice. What else? Any questions over anything? Yeah, you guys are good. Um, so we finished up, we did Mars last time. I think I kind of asked you guys to think about whether you thought Mars was a cool place to live. Anybody signing up to be on the first spaceship to Mars here? Do you guys have any thoughts about that? Anybody roll it over in their head? Mars versus Venus versus, yeah, Dante.
Um,
What do you think?
I've I've thought about it quite a bit, whether or not like uh more like Venus or Mars would be a better choice. Mars makes more sense if our goal is to make a staging ground to go further, cause then away
It's in
from
the right direction. Yeah, I like that.
rather than going closer. Also, I feel like humans would have a better and easier time dealing with at least in terms of actual people, getting them on Mars rather than having any humans be on Venus.
The surface, yeah, for sure.
Um,
Yeah, Venus would crush you to death and cook you, and it's not a very friendly place.
so yeah,
Any takers on Venus? What do you think, guys? Yeah.
Venus is just inherently more hostile, it seems. Like there's still problems with living on Mars, but most of that comes from a lack of things rather than things that are inherently harmful in their existence, like Venus, where just being there is a major issue, aside from we can put someone in a box on Mars, probably with relative like consistency. It will be difficult to
Yeah, they have to float in the clouds on Venus in order to even pull that off.
a lot harder to manage.
Mars is rough though. That soil is really, really bad news. Yeah.
Even if like I feel like even if they like found Mars to be like habitable,
Yeah. They have not.
but theoretically if they did, hypothetically, I feel like I mean I don't want any part of it because it's like you have to think about like adaptation and how like we adapt to like global warming and excessive like CO2 levels. And I feel like it would just be like such a like if we just like moved there, it would be such a shock to like us as beings.
Mm-hmm.
I feel like we wouldn't have like time to adapt.
Mm. Yeah, yeah. It's yeah, space is rough. This is good. I'll get you then you, yeah. Tammy.
So I think that Mars would be challenging because of the dirt, like you said.
Yeah, it's the roughest part as far as I can tell.
It feels like it'd be like sand, and so then you're just like stuck living in this like box or like
Yeah.
biodome,
Yeah.
and it just seems like how it just seems always like terrifying to me that you're just one like
Yeah.
picture of the biodome away from.
that's anywhere in space.
I know.
That's anywhere.
Well, so far.
Yeah, it's far away from home too. What were you gonna say?
I just think that they both sound kind of miserable.
Yeah, they do.
Like Venus, you're gonna be in your little like blimp home
Yeah.
forever.
Yeah.
How can you interact with other people
Yeah.
and get between those?
Yeah.
And then on Mars with the like poisonous dirt, you can't just go outside and take a walk and then go back inside and you're good. You're gonna have to do like the extensive cleaning process. You're gonna have to make sure that like you're I don't know, because you're gonna be in a suit and it's not gonna be as like refreshing as it would be here. I just feel like as humans, the way that our minds are sort of built to want that sense of comfort, that sense of peace, um, where we're at is kind of the only place we can do that currently.
Yeah, this place looks really nice the more you compare it to everywhere else. Yeah.
I think that honestly, with of I think with Mars, the majority of its issues are no different than the ones we dealt with on the moon, other than that it's much further away.
Dirt's
And
worse.
I don't think we'd ever get to Mars before we've gotten having an actual foothold on the moon that's semi-permanent like the ISS. Before we have that, I don't think we could even think of going further to Mars. But again, I feel like the majority of our stuff that would be built on Mars in the future, one wouldn't be by humans, just by virtue. I feel like we would have built stuff and then put humans there in terms of humans that would stay.
Mm.
Maybe we have a human or two there for like, oh, look, the first human that set foot on Mars, and we take them back.
Mm-hmm.
But I feel like it's going to just be a very, like, people talk about how sudden, and rightfully so, how sudden any move like that, moving to a different planet would be. I do not see any mass migration to another planet happening anytime soon.
Yeah.
I feel like it would be a very gradual, probably not, I mean, we won't live to see the future of it. It'll take centuries probably for us to have a genuine settlement there.
Yeah, I would agree. I would totally agree.
I don't think Mars is the place.
Yeah.
No, so Mars, and I wasn't here last week. If I state something incorrectly, please correct me. But like Mars is a relatively static place or undynamic when you compare it to Venus, right? Venus is this sort of volatility on the surface. It's at least as far as
It's definitely a desert compared to, fiery
right
pressure box.
There's the heat, there's the pressure, there's the sort of volcanism that we assume is there based on what we know. But on Mars, you don't have that kind of volatility, right? I feel like first of all, colonists are a different breed of human.
That's a possibility too.
And I feel like the first implementation of some sort of colony is going to be an industrial facility of some kind. It's either going to be resource extraction or production of something.
There's people lined up to go to Mars, by the way, for what it's worth. There's people lined up to go to Mars.
Oh,
I saw a profile of some NASA selected some young lady.
But my point is, when you're looking at an industrial process, the practicalities of colonization are priority one, you have to be able to produce energy.
Mm.
Without producing energy in a stable way to produce electricity, you either have to bring it with you, store it, or find a way to produce it when you get there.
Probably a little bit of both, yeah.
And in the volatility of Venus, if they can stabilize the buoyancy sort of mechanism, then the ability to produce energy on Venus seems like it would be easier, more controllable. You'd have like geothermal, or you'd have something that you can utilize out of pressure.
Yeah.
To fund or power whatever other, your water production, your food production, all that stuff.
Yeah.
Your life support system.
Yeah.
Doing that on Mars means you have to take everything with you, along with all of the other problems.
It's true. It's true.
So from my perspective, it seems like Venus is the winner.
I'd like to also add the possibilities we shouldn't be restricted to just Venus and Mars.
Yeah.
Also, the moons of Jupiter.
And we're going to get there today.
Maybe Titan.
Maybe. Hopefully we'll get there. Yeah, so I have an ambitious class for us planned today where we're going to basically polish off. Yeah. We're going to polish off another third of the solar system today, but we will talk about those possibilities. They're intriguing for sure. Yeah, Dante.
I think you also left us with whether or not you thought terraforming Mars was impossible.
Yeah.
I feel like it probably is, again, not in our lifetime.
Yeah.
Probably 4 centuries or something like that before it's done.
Yeah.
But I feel like the first order of business that would have to be done is to be able to generate a magnetic field.
Yeah. We kind of stopped on that.
I feel like the satellite solution, which was something that I looked into after it was mentioned in this class, because I've never heard of it.
Yeah.
It was kind of genius.
I mean,
there's a lot more progress on that than I thought there was. Not that it's like, oh, we have it now.
The idea makes sense, yeah. The material science, I think, is lacking is the problem.
Yeah.
So we can generate really strong magnets already, but the spatial extent of it is the problem.
Yeah, once we figure that out, I feel like most of these problems are limited by a current just general science block.
Yep.
And once we have a breakthrough, and
I think it's cool to work on multi-generational problems too, you know? It's
Yeah.
like, plan things that are going to take 1,000 years. I like that. There's something intuitively that speaks to me about that, and I think you're right that the moon is probably the best place to figure everything out at. It's probably the best place to assemble and build stuff. And then, yeah, you want to work on Mars? You can work on Mars. You want to work on Venus? You can work on Venus. You know, these are our best places to test things out because the next stop after those is really far away, right? So even, Corey's brought up that we could maybe go out to the moons, right, of Jupiter and Saturn. They're really, really far away. They're really far away. I mean, to the point that phoning home would have such incredible delays, it would be hard to have a conversation. So, that's light speed communication, right? That's really tricky. Yeah, Ezra, what were you going to say?
So about Mars,
Yeah,
we all know how well we're not really like taking care of this planet.
there's an issue too.
If we were to actually like terraform Mars, it would only give us a couple extra centuries. Like I assume, let's say we're moving to Mars because Earth is becoming uninhabitable or something.
Yeah,
It's only going to give us a couple of hundred more centuries before.
it's a really good point. Did anybody see the HBO series The Expanse?
I was about to bring that up. I
It was on
haven't seen
Amazon.
it.
Those of you who've seen it are like, yeah, absolutely. But it's funny because it's basically like they export all of Earth's problems to Mars. And, of course, who are the people who are going to end up on the desert hellscape? It's like, well, the minimized sort of populations from Earth, anyways. And yeah, I think it's a really good point. I mean, I don't think that people are saying we're going to go to Mars because we've ruined Earth. I could see how there's a subtext to that, but there's a huge problem. It's like if we can't figure out how to get along on this planet, we're just gonna keep having these problems go off, and they're gonna be even more dramatic, let's say, and more catastrophic because we're miles and miles away from help and blah blah blah. So,
Exactly. If the problems don't get fixed here on Earth first before we go somewhere else, we're just going to spread those problems more.
I agree, yeah, but at the same time, I didn't get to we didn't get to look at this too closely, unfortunately. But we do get hit by asteroids a lot here, actually. So we get hit by the equivalent of like a Hiroshima size explosion in the atmosphere every year, pretty much. It just usually happens to be over the ocean, up in the sky, really far, over Siberia. Um, it's not unreasonable that maybe we might want to diversify our interests in the solar system. So it's kind of, I agree, it's in some sense weighing the practicality with the need to back this place up a little bit too. They're both really interesting poles of the argument. Yeah.
I was gonna. You mentioned The Expanse. I haven't seen the show, but I did see. I remember a signing report about one of the key like plot points in that show, which is the creation of direct thrust travel. If you don't know, basically we discussed like we need gravity assist to be able to send things, and it would take like 8 months to get to Mars on a good day. Um, and we also talked a lot about misunderstandings with fusion and the basic fundamentals of how atoms work. If that gets figured out, if the fundamentals of science, if there's a breakthrough there, it's not hard for me to imagine that could be a breakthrough in energy production or in efficiency.
Yeah.
And
I liked that about that
when
show
that
too, actually. Yeah.
it's not that impossible for me to imagine a nuclear fusion powered craft
Yeah.
that could, and if the direct travel was there, it would take only a couple of days to get to Mars, and that would make a lot of these problems go away significantly.
Yeah, I think that we haven't quite mastered the atom as well as the advertisements would say maybe. And so I thought that was a really good point in that series too. It's like if we understood how these things worked a little bit better, maybe we would have wildly different technology, and I think it's possible. I mean, I'm not sure. Yeah, that series is pretty good up until they start going through like time warps and stuff. At the back half of it gets a little weird, but
Season 1 and 2. Season 3 gets a little wonky.
yeah.
Back season 4.
Are they still putting them out now?
Season 6 was, I think, the last season,
There we go.
and that's sort of like complete.
I mean, I really do enjoy like it really speaks to what Ezra was saying, which is kind of like, are we gonna still be doing the same tribal warfare stuff, 5,000 years in the future when we're spreading out through the solar system? That would be a real bummer.
Probably.
I'll take the optimistic camp and say we'll figure it out by then, but maybe.
I doubt it.
So, any more thoughts about Mars before we keep cruising? Yeah.
Not necessarily about Mars, but Jupiter's moons actually are like an interesting pick because I think one of them is thought to have an ocean under it.
Hold on to that because we're gonna get to Jupiter's moons if we're lucky, if we make it that far.
If we start now.
If we,
I mean,
well, I'm not gonna be able to talk about all the moons of Jupiter and Saturn, but there are some really interesting ones, and hold on to your thoughts and speak up when we get there because I want to throw some pictures up so we can talk about it because I've probably got some cool pictures so that we can look at them while we're talking about it.
I'll say something about the radiation at least. So if the radiation can be dealt with on Mars, I feel like one of the issues with Jupiter's moons is that they're blasted with radiation. Surely something could be done. If we have the technology to do it on Mars, I'd assume there'd be a way to do it on Mars.
Yeah, I think local radiation is not too big of a deal. Radiation can be shielded with magnets pretty well. The radiation on the surface of Mars is, I think, less than the space station, if I recall correctly. So it's not great, but it's not the end of the world either. I think these things can be dealt with, but yeah, those moons have some appeal, particularly if it turns out that they have really nice oceans under their crusty, dirty ice surfaces. So let's check them out in a second. Since basically I want to talk about Jupiter and Saturn, and I'm going to talk about some of their more interesting moons too. But we're basically going to blast through the asteroid belt because we are leaving Mars. We're going very, very far to Jupiter next. The asteroid belt, we don't have time to really dive into it today. Very little is known about it, actually. And so I'm going to skip over that. I will say that it's actually not probably what you're picturing. There's something on the order of hundreds and if not thousands of kilometers in between each of the asteroids. So it's not like Star Wars where you're dodging these asteroids when you're driving your spaceship through it. It's actually quite sparse, but there's a lot of debris there. And some of the pieces of debris, the asteroids, resemble small planets. And of course, this is where you get into the crumbling line between planets and asteroids and then stars too, right? So that's what's, I think, the fun part about today's discussion, at least from the natural history perspective, which I thought I might open up with, is just to kind of point out that so far we've been talking about these little rocky planets, right? Which in some sense are on the order of the size of the cores of the much larger planets that we're going to be talking about for really these last few lectures. And the big planets, these Jovians, Jovian really just refers to Jupiter. And Jupiter is, of course, the king of the gods in the Roman tradition. These things are actually kind of on a continuum with suns going all the way back. What's that?
Oh, I just said, so of course we named the biggest planet it.
Of course. Yeah, well, everybody did that too. I'll point some of that out in a second. But I think one of the things that's this is, I think, one of the biggest shifting paradigms in all of planetary science right now. And I think we'll basically end up writing a book about this next, actually. But these things are on a continuum. They're all sort of made out of the same stuff. Stars are basically, on balance, they're mostly made out of hydrogen and helium with a bunch of more, some heavy stuff, as far as we can tell, that makes it into the atmosphere. The dividing line between, a low mass star and a brown dwarf really gets kind of nebulous. I've pointed this out before, but I'm going to say it one more time. really, the difference between a low mass star and a brown dwarf is whether it can fuse regular old hydrogen, right? So brown dwarfs can actually do some sort of fusion. They're heavy, they're bigger than Jupiter's. They kind of draw the cutoff line around 13 Jupiter masses for a brown dwarf. And they can do fusion of heavy hydrogen, but they can't do fusion of regular neutral hydrogen, light hydrogen. So not quite big enough for that. And then Jupiter's, after that, that cutoff line, which is somewhat arbitrary, but not entirely, you get Jupiter's, and Jupiter's can't do fusion at all. So Jupiter-sized planets. Now, traditionally, and I don't remember what your textbook calls them, but usually in the past, people called Jupiters, these Jovians, they call them gas giants. You guys probably heard this before. Turns out to be an increasingly inappropriate name for them. In and of the fact that while there is some gas in their atmosphere, their body is actually in a very different state of matter, which is, somewhat between liquid and solid. Like actually, it's quite dense, and actually the models of the cores of these things is rapidly evolving right now, and I'll point out some of that really quick. But what's interesting is just that all of these things are kind of on a continuum together, which, from where I'm sitting, opens up really fascinating possibilities about their metamorphic relationship to one another. Could a Jupiter-sized object have been a brown dwarf at one point in time? Or will it be a brown dwarf perhaps in the future? Could a brown dwarf have been a star in the past that lost too much mass? Or will it perhaps gain enough material to be a star in the future?
Robert, can you go back to the previous?
Yeah, sure.
I just want to clarify something because this slide seems to have an implied scale. There's no metric there.
Yeah.
You mentioned at one point just in passing, the brown dwarfs have on the order of 13 Jupiter size. So this image that we're seeing here, this is not the scalar, this is not the progression size. This
is what's kind of interesting. Size is a really confusing attribute because what really matters is density.
Okay.
So density is how much stuff gets crammed into how much volume. And remember, volume scales with a cubic, while radius is just going to be a linear scaling, right? Or even, so you can actually ramp up your volume really quick by just expanding a little bit. You can also, and density is a volumetric measure too, because you can cram more stuff in there. So it is possible that this scale is appropriate that we see here. It's just that maybe more stuff is crammed into that brown dwarf than is immediately apparent to you.
So
it's more.
It's not 13 diameters.
Right.
Jupiter size.
Exactly.
It's
all about how much material gets squashed into one place, basically, at the end of the day, because that's what it's going to take to create that homogeneity to squish and do the fusion processes, however it is that we model them. It really comes down to how much stuff is in one place.
Right.
Yeah.
Thanks. Yeah, this was just when you said it 13 times, my brain just
Yeah, it's kind of weird. Yeah, I still stumble over that one a little bit. But you have to think more in terms of how much stuff is squished in there. So, I'm not sure that we needed to go over this. Gas giant, brown dwarf, we've talked about that. The ice giants we'll get to next after we leave these guys. That'll make more sense next semester. There's another piece of the puzzle too that's really fun, is that since they built this next generation telescope, this space telescope that they park at the Lagrange point, they found these really cool phenomenon that nobody could have expected, which is these pairs of Jupiter mass objects that are orbiting each other, dozens of them, without any star system attached to them. And I think nobody expected this to be the case. So, there's essentially a few ideas about where these brown dwarfs come from, or Jupiters for that matter. And this has really forced people to rewrite it, because generally speaking, most people figured that brown dwarfs were fully explainable by being on the way to becoming a star in its own star system, forming a solar system, but they just didn't accrete enough material. They didn't collect enough material. That story gets really bizarre when you're talking about low mass objects like Jupiter's, especially them orbiting one another. I think it's really, really starting to build in the direction of these things being on some sort of evolutionary continuum together. You know, I really like the parallels to natural selection too. I know you guys probably aren't taking any biology or anything, but if you remember back to high school or something, this theory of why creatures look the way that they do, it involves this selection process, right? It's kind of, you know, and there's details about that story that I think are not fully developed, but the basic idea seems to make sense to me, at least. Maybe it makes sense to you. It's like sort of experiments in biology that don't work out sort of don't get perpetuated in some sense, right? It's like if you have like an extra arm or something that's not doing anything, it's unlikely that it will give you a selection benefit into perpetuity. And you, probably after, you know, so many generations, like the creatures won't have that extra arm. That's kind of the idea. I think the same thing might be emerging in the case of planets as well, where it's like some of these planets that didn't have some of these bodies that didn't have the right circumstances. Maybe they formed in a part of the star forming nebula that didn't have the right materials for them to condense out, and maybe they didn't form stars as a result of it, and they formed Jupiters instead, like as these little condensation reactions went down. Right? It's very difficult to gravitationally explain the formation of these rotating Jupiters by themselves, but there might be other selection processes that tend you towards being a Jupiter versus a brown dwarf versus being a star. And the same could be said of some of the rocky planets if you take this to its logical conclusion. It's like, why does Mars and Earth and Venus, why do they all sort of resemble each other in some ways, but they also seem to have different features? They're wildly different in many ways, especially looking at them from the outside. And why is that? It's like, well, maybe they were selected differently. Maybe they were subject to different pressures during their development. They were, you know, further away from the star that they developed around. Maybe their starting materials, wherever they developed in whatever nebula, wherever, were wildly different. And so this environment, in some sense, enforced what eventually became what we experience as those planets at this point in time. It's, we'll circle back on this because the standard story that all of our planets formed kind of more or less right where they are as they are is, I think it's kind of inadequate in some sense, especially when we start thinking about these density problems. And most people, I think, are starting to realize that, but the future forward is a bit unclear, I think. Yeah.
It just because in my head, and again, you kind of touched on it at the end there, but the standard story I think that I was told
Yeah.
is the solar system evolves or develops like, and this is a generalization, right? Not just ours, but
Yeah.
solar systems develop in time together.
Yep.
Star form,
Yep.
and then the planets form around,
Yep.
sort of in this very orchestrated sort of pattern.
Uniform process, yeah.
And then we've had these conversations before where like our solar system, people start to talk about the formation of it. There's always another planet or another celestial body that's impacted and caused this other event to happen.
Sure.
And it's like, well, if we formed all at one time and in these stable orbits, how does that happen? And this seems like a much more viable thing where if all of these planets are developing next to stars in these independent systems in a much more unstable, chaotic environment, and our solar system is a model of, well, it's been around for such a long time. This is what a stable system looks like after the chaos has sort of run its course, right? Is that kind of what we're getting at here?
I mean, I guess I kind of assume that you guys have read the textbook already and kind of gotten the 30-year-old explanation or 300-year. I mean, it's a 300-year-old model. It goes back to Laplace and Kant, who are these philosophers essentially. back in the 1700s who came up with the idea that the solar system kind of all forms together out of this swirling nebula.
It's Kantian?
It's Kantian, yeah.
Oh, hey.
We'll talk about it on the last class because I'll kind of run you through all of this. Well, I'll try to zip all this together, but I do think that it's an inadequate story in many ways, but I think that we've grown really comfortable with it. But I think that all of, from this kind of thing, we're going to talk about the transition between Neptunes and super Earths next week. Actually, after Thanksgiving, we'll do that. We'll talk a little bit about these Jupiters that are transitioning into more Venus-like looking planets today because they're getting their atmospheres cooked off. I think that there's a metamorphic theory that is at least extremely rational and congruent with the data. Again, when you're talking about stuff that happens billions and billions of years in the past and occurs over this timescales of millions of years, you're going to be pretty well lodged in a theoretical space forever. So I'm not here to tell you what is or what isn't, but I think that there's a different perspective, which is more metamorphic, that appeals to my intuitions about these things a bit more. And I think that the literature justifies that to the extent that, sorry, my computer's just decided to install some new software. That's not good. Don't install. All right, so yeah, I think that I think there's a metamorphic history. I think the main barrier to that is the extraordinarily short timescales that are granted to us by standard cosmology, and unfortunately, we have an entire course next semester devoted towards standard cosmology, which is unfortunate that it's not all part of the same class or something, because of course when you teach cosmology, it's very hard for people to understand who cares, why does this matter? And it's like, well, it matters because it constrains our theoretical space for how we explain the things we see in our own solar system, including our own planet. So I think that we're on the verge of a really beautiful paradigm shift. It could take 100 years, it could take 2 years, I really don't know. But I do know that the continuum is possible for a lot of these, and yeah, as we start to let's check out Jupiter and Saturn, because I think in some sense they're very similar planets, but they have different levels of developed chemistry in their atmospheres, which kind of suggests that maybe one is more evolved than the other. But yeah, I think it's an interesting story because in the end of the day, all of the planets in our solar system are really, really, really different from each other. Even the ones that are similar are, like, closer you look at them, the more you're like, what the heck is going on? Like, Uranus is flipped on its side. We'll deal with that in a second. But Venus, yeah, it's kind of similar to the Earth, but it's rotating the wrong direction, and its atmosphere is completely this just sort of smog factory, just nightmare. Mars too, right? It's got like the iron, it's got an ironous, it's very core-like in some sense, but they just don't seem to be from the same party necessarily. It's very, very interesting. The more similarities you try to find between these planets and their histories, the more their histories tend to naturally separate out. Do I want to say anything about this? Not really. We're going to get into too much details, and I'm going to come back to it. Because I want to make sure that we have time to talk about these moons today. I mean, this is a paper that I found just today, actually, where people are starting to reconsider the idea. All right, so they had this huge problem, right? I've brought this up many times. How in the world do you accrete something as dense as the Earth from basically a swirling pile of gas, right? It's a sort of intractable problem in some sense. The same problem actually exists for Jupiter-like planets too, because they are thought to have really giant cores, not giant, but very dense cores as well. It's kind of interesting now because the model, the sort of new popular idea is that, well, they didn't accrete the really heavy cores first. They sort of collected all of these metals which exist in this kind of fuzzy blob state inside of them, and then as time progresses they kind of condense and accrete and become basically these big rocky metallic core-like things which define many of the planets that we've talked about in the last few weeks, essentially. I mean, if you think about, we started with Mercury, it's basically mostly core. Mars is a pretty large piece of core. And all of these rocky planets have these huge amounts of iron and nickel, which is just incredibly dense, difficult material to form into a sphere. I mean, yeah, you should try to take a piece of iron and work it into a sphere sometime. You know, it's not so simple to accomplish, and certainly not simple for gravity alone to accomplish. So this is kind of a cool trajectory that I see happening in the literature right now, where people are starting to imagine ways to make these cores from condensation reactions inside of these giant planets, basically. Yeah.
I just wanted to mention heat because if you ever try to, form metal into
You will need heat.
probably want to heat it up to make it softer.
You will want heat for sure. And heat's actually a really funny puzzle too. So, in case I forget to mention this, when they were trying to figure out how to power the stars, we'll spend a lot of time on this next semester, but they were trying to figure out how in the world the stars were so hot. And engines were brand new at the time, right? Heat engines. So the whole field of thermodynamics was being born. But basically, they realized if you squeeze stuff that you could heat it. And so they're like, oh, great. The stars are just big. They're squeezing stuff. It's getting hot. And this is actually called the Kelvin-Helmholtz mechanism, named after the two super bosses of thermodynamics. So they went with that for a little bit. And then all of a sudden, people started crunching the numbers and they're like, oh no, if that's true, the sun should burn basically the sun couldn't be more than a few millions of years old. Let's say tens of millions of years old, and it'll be gone really soon. So they said that wouldn't work. And they actually didn't have a way to power it for a very long time. But back to our planets, Jupiter and Saturn today. Actually, Jupiter, they think that it does actually heat itself with this compression mechanism, right? Saturn, however, has more heat, which is weird because it's smaller. It actually gives off 2.5 times the amount of light that it receives. By light, I just mean electromagnetic radiation. Than it receives from the sun. And it's a bit of a puzzle, like why there's this disparity between the two, because if it was just based on this contraction thing, well, Jupiter should be the one that's generating the more heat and the more light as a result of this. So people have been toying with ways to make this happen. And a lot of it, I mean, the mechanisms, I'm in no position to evaluate them, but, they range, I think the most popular one is that there's some sort of rain that generates a lot of friction, actually a helium precipitate that kind of rains down out of the atmosphere and generates a lot of friction. I don't know if it's true or not, but it is very, very bizarre. And this people are always coming up with new and interesting ways to heat up things, but the balance is very, very mysterious and strange between these two bodies. All right, let's make our way. If I had more time, we could do more brown dwarfs. But if anybody sticks around next semester, we'll do lots of brown dwarfs because these tie into our story of suns really well. Another thing that's been quite interesting is the hot Jupiter story. So this has been developing the last few years, where as we find more of these exosolar systems that we study, we find that, we've found a lot of these things we call hot Jupiters, which basically means a Jupiter close to a star, way closer than our Jupiter is to our star. I think our Jupiter's at 30 AUs away, so 30 times the distance from us to the sun. Very far away, very cold out there. A lot of the Jupiters that we've found out in other solar systems are really close to their stars, which is really interesting. It might be a selection bias because the things that are closest to the stars are gonna make the biggest shadows, and that's basically what we see. But it's fascinating because what's happening to these planets? Well, they're getting their atmospheres stripped away at extraordinary rates, right? You can just imagine it's just getting photo-evaporated. It's like if you took a snowball and put it next to a fire, right? It's just going to evaporate the thing. So they're seeing these transformations of these planets, and you can imagine that one of the best ways to accelerate the change in appearance, one of the best ways to accelerate chemistry is to apply a flame to it, right? I had a really good advisor when I was in grad school who really impressed upon me that heat and time are kind of the same thing, right? When you heat something up, you basically speed up what would happen naturally anyways, right? So you can imagine in many ways, and it's not a perfect analogy, but it is kind of true, like heat being the molecular motion. If you apply a lot of motion to a system, you're going to kind of get where it was going to go eventually anyways, entropically, but you're just kind of rushing it along. And so by putting these planets right next to the stars, you can imagine that they're going to change form really, really quickly. So I think there's going to be a lot more work coming out in that dimension soon enough. You know, this is kind of fun. So if you look at Jupiter in the infrared, it actually looks a lot like a star, which is really, really fun. And not only is it fun, but I think that it sort of exposes the reality, which is that this thing is generating a tremendous amount of heat. It's not in the visible range anymore, but it is radiating like a black body, much like the surface of the sun. And, you know, by side, I should have pulled a picture of the photosphere of the sun. It really, really intrigues the imagination about their former natural histories. You know, I think in some sense, one of the most fundamental features of the story we tell in the textbook right now about the solar system is something along the lines of everything is very predictable and gradual. And I think that the reality of the picture we see about our solar system is that weird things have happened suddenly in the past that are very difficult to put a gradual story onto, you know. Even whether it's conceding to planets sometimes just get hit by other planet-sized objects and puts a crater on top of them the size of half the planet, to this one gets in, you know, its spin is completely inverted or flipped on its side or something. Like, it seems like the reality of the natural history of many of these bodies involves really sudden punctuated equilibrium. You know, everything's chill for maybe 1 billion years or two, and then something crazy happens and it changes wildly. Could something like that explain the transition between stars and Jupiters and brown dwarfs? Yeah, I don't see why it couldn't. So, Jupiter. Yeah, I mean, Jupiter is the brightest after Venus and the moon and yeah, the sun. It's the brightest object in the sky. Who's seen Jupiter up there before? Oh, cool. Nice. Yeah, again, I recommend if you ever get a chance, get some binoculars, put them on a stick so they don't shake, and check out Venus. Or sorry, check out Jupiter. It's really cool. With the binoculars, you can actually see the little moons going around it, and we're going to talk about a couple of those moons today. But it's super profound. People have been observing this thing forever, and they generally associate it with their chief deities. So, like we said, the Romans associate it with Jupiter. The Babylonians associate it with Marduk. We didn't get to talk about Marduk enough in this class as we have perhaps previously. But Marduk was their central deity. They named all of their kings. They basically had god kings that took on the likeness and responsibility of being Marduk. So they named all their kings Marduk. Marduk this, Marduk that. The Chinese called it the year star because it would basically move one zodiac position every 12 years. And so in the Chinese calendar, these zodiacs are actually new positions. So that's interesting. The Jupiter goes around the sun really, really slowly. But its day is really, really fast. So its day is on the order of hours. The thing is spinning incredibly, incredibly fast. So, if you were to put the Earth next, oh, is that a picture? No, that's a moon. I was going to say the Earth is, maybe a little bit larger than that moon over there off to the side, but the Earth is spinning, of course, over the course of 24 hours, which is relatively slowly for a small body. This thing's enormous, and it's turning on its face every 10 hours, which is just bananas fast. What about the inside of this thing? We've kind of alluded to it a little bit. This is also a really fun piece of the puzzle too, but honestly, the most exciting pieces of Jupiter's natural history relate to the changing paradigms about stars themselves. Like I said, when I was a kid, and I don't even know, I haven't checked your textbook in a while, but they would call these things gas giants, right? That has certainly been walked in a different direction recently. People realizing that actually on the pressure and temperature diagram for hydrogen, let's just say Jupiter's mostly hydrogen, helium-2, which are, of course, the smallest and most simple atoms At those conditions of pressure and temperature, a large portion of the deep part of Jupiter is in some sort of strange liquid phase. And actually, it turns out if you apply enough pressure to that liquid molecular hydrogen, it turns into a kind of conductive version. It appears to take on some sort of metallic-like properties, which are poorly understood because it's difficult to achieve these pressures for any lasting time period here in a laboratory on Earth. So it's in some sort of weird condensed phase inside of it. It's a very, very strange world. But some of these pressures are actually applicable to the surface regions of stars too, or at least within a few kilometers of depth of stars too. And so I think that the really fun part about this story will play out when we start studying next semester how stars do their magic and what stars really are. Because the same way that we used to call these gas giants, I think that the standard picture of stars as giant gas balls is probably going to prove inadequate as well pretty soon. But it relates to what we know about Jupiter's, and of course we can get much closer to Jupiter than with our spacecraft than we can to the sun right now. And so it's an interesting test bed in that it's a sort of cooler, safer version of the same material reality that the sun is itself, which is quite fascinating. It's almost like a safe little sun. Yeah.
Just clarifying, because I know that there are things that you've talked about before that you always have qualified with. This is incredibly heretical in standard model.
Yeah.
And we're talking right now against about like this liquid. I don't know if it's the liquid metal hydrogen.
Yeah, it is. It is. It is same stuff.
Aromatized stuff.
Right.
Is what we're seeing with Jupiter here, like this model that you're describing now, is this a part of like our standard cosmos?
Yeah, it is actually.
Now?
It is, yeah.
Then, so we talk about how Jupiter, as a part of the standard model, it might be a failed star and has this core, the central structure. But then, as soon as we look at the sun,
yeah, it's weird. It's really weird.
There's not. So that connection has.
Yeah.
Been
I don't think that anybody thinks our Jupiter is a failed star, but I think they think other Jupiters are perhaps failed stars.
They're calling them hot.
It's like stitching all these pieces together.
Crazy.
It is a little crazy, but I think we have to be forgiving because the reality is all textbooks are about 30 years behind where the scientists are actually at because the scientists can never agree, right? So we're all sitting out there arguing about this, that, or the other thing. And the person who's at the highest chair, whose theory was popular 30 years ago, they're still at the top of the academic place, and they're going to hold on to it till they retire or die or whatever. So yeah, there's a lot of contradictory pieces of this puzzle. It's pretty bizarre. I mean, the most bizarre thing, I don't know how much we can get into this because we're not really dealing with stars today, but yes, people generally accept that liquid metallic hydrogen exists at some depth below Jupiter's apparent surface. In terms of why that same understanding isn't applied to the sun, it's more convention than anything from what I have.
Sort of the central point of the question.
Yeah.
Just clarifying, because we're putting this up as a model, is this the standard?
This is,
or is this a part of the?
This is, this is nothing controversial about this piece.
Sure.
Yeah. I'll be, that's why I'm staying away from the sun because I want to build that out really carefully so that people understand what's understood versus what isn't. I actually think that it's a pretty small tuning too. That most let's say astrophysicists I talk to, they think about the sun as made out of plasma, and liquid metallic hydrogen is actually a type of plasma. It's a one-component plasma. Plasmas exist in both liquid and gaseous form.
Yeah.
So they can keep their word plasma. They need to just stop acting like it's a ball of gas in order for a number of things to click into place from where I'm standing. But
I wasn't trying to divert.
It's super fun. I in some sense, it's my favorite subject, but this semester is a tour of the solar system. So without talking about the sun for some reason,
One thing that always urged me whenever I heard about gas giants, when I was younger was, well, if they're gas, can't you just fly through it?
Mm,
Like if it doesn't get dense enough, because if it gets too dense, well, it's just liquid. Because if it's not gas, you can't fly through it. But then, so I just kept hearing, well, but gas just gets so dense there, it doesn't need to be liquid. I'm like, but that's not how it works.
it is weird, yeah. The same thing applies to the sun too.
Yeah.
It's very actually it's very you guys are gonna have to help me out because it's very difficult for me to not just start talking about stars because the things we learn, in my opinion, what's so fascinating about Jupiter and Saturn, other than the moons, which we should save some time for, is that they're basically like little star laboratories. Like they are like tiny little versions of stars that aren't quite gonna be dangerous to fly near, right? They're basically made out of all the same stuff. They have a lot of the same features. And they just seem to be in a different, somewhere on a different track of evolution, the way I'm looking at it. Um, whether or not they spent any time as stars or will in the future is an open question that anybody could argue about, given the time, enough time or radical step function events that couldn't be predicted. But they are really, really similar in composition and in many ways, yeah, in behavior as well. Two stars, which is really fascinating. That's why I love this. I was so excited when they found these pairs of these Jupiters just without solar system. It's like sort of fit into my understanding a little bit better. Especially because, by the way, I forgot to mention they found those pairs. Where did they find them? They found them in the same region of the Orion Nebula where we find the most stars being formed too, right? So it's like there's some sort of cool news story coming on with these. I can just sort of taste it in the air. All right. I'm not going to talk too much about exploration of Jupiter. We've sent a lot of robotic probes out there. There's no real surface to speak of to land on because what you just have is this transition from an atmosphere to a kind of liquid-like uh, environment, and so I don't think it's likely that we'll be walking around on Jupiter anytime soon. It has a pretty strong magnetic field, which is pretty rare in the solar system, from what I can tell. Uh, what else do we want to say before I go on? I want to talk about the moons, though, mainly because I think they're most relevant to humanity and perhaps most interesting. And Saturn's got a couple of really cool moons that we should talk about too. First of all, see if you can see this here. Can you see the direction of the arrows here? Okay, so the big moons are called the Galilean moons. Why are they called the Galilean moons?
Because they're the ones he saw.
That's right. Yeah, Galileo saw the moons with his telescope, and I think he tried to name them after the Medicis, if I'm not mistaken, after his sponsors, basically. Somebody intervened, I forget who it was, and decided no, they would be named after Greek mythological creatures instead. What's interesting is they rotate one direction. Then there's another swarm of moons. They're much smaller, but they orbit in a different direction, which is really, really bizarre. When we get to Saturn, hopefully I can point out that the same thing is happening at Saturn, except there's pockets of moons orbiting in different planes as well, and in different directions. I point this out only because I think that it fits into this picture of these bodies having been through some natural history which is entirely unpredictable to us. I think that it's highly likely that these moon systems evolved in different steps under different fashions. And I actually know a guy at Caltech who tries to come up with these uniformitarian models, and to his credit, he has been able to bash the equations around to the point that he can make these moon systems happen out of a steady state system as well. So that is the textbook story, of course. We'll circle back on that for our last class to make sure that we can compare these two ideas I've been developing throughout this course. But I want to talk about Jupiter's moons because they're quite interesting, particularly two of the Galilean moons. I figured I would just, I guess we'll zip through the 4 Galilean moons, and we'll get over to Saturn and check out at least 1 or 2 of Saturn's moons because they're really interesting. First of all, these moons are orbiting in a really beautiful resonance, right? So every time one goes around, it sort of gives the one behind it a tug. And so they have synced up in this really harmonious fashion, right? They're basically octaves of each other in the musical sense. The first one out is this really, really bizarre moon called Io. And Io kind of looks like sort of like some stinky cheese or something. But the reality is that it is quite it's quite a hot and volcanic place. It's actually got something on the order of several hundred. I guess there's 400 cataloged active volcanoes right now. They're changing kind of day to day, which is quite interesting. Um, and we've got some really beautiful pictures of this thing recently. This is actually, I think, an assembled version. IO does something else which is really crazy, which is that it's got so much volcanism on it that it's literally spewing out these particles into the orbit of Jupiter that are, in a sense, deforming Jupiter's magnetic field because they're charged by virtue of the fact that they're flying into this frictional stream. They're getting charged. These particles are warping and extending, actually modifying the spatial extent of Jupiter's magnetic field. This was actually something I wanted to bring up with respect to the idea of putting a magnetic field around Mars. You know, the big challenge that I can see, like I said, is not that we can't make really powerful magnets. We can. MRI machines are incredibly powerful magnets. The question is spatial extent. So could we use some sort of, and I've heard a proposal, although I couldn't find the reference for you, but I heard a proposal at some point of taking one of Mars's little dirty potato moons. Remember those tiny little moons, if you even want to call them that, these big asteroids that orbit it. What's that?
Phobos and Deimos.
Yeah, Phobos and Deimos. One idea was like to sort of ionize the surface of these things somehow. So you send a bunch of charged particles out and you can maybe extend the extent of your magnetic, you have an artificial magnet, and you use this orbiting stream of particles to sort of draw out the extent of the magnetic field that way, which is interesting. I think we should pay attention to how Io is doing this, because while it doesn't make or amplify the magnetic field, it does change the shape of it, which could be really useful, because I think that's the biggest problem for the Mars artificial field.
Yeah, I assumed that you were going to get to that because this is the comparison that I read in the study I looked at was about Io having these charged particles that just increases the spatial dimensions.
Yeah.
The reach of Jupiter's magnetic field and its shape, but doesn't change its strength.
Did anybody mention that with respect to the Mars artificial fields?
Their idea was like, well, what if we make basically on a smaller scale, we make, satellites and positioned within certain gaps in Mars's current magnetic field that are magnets. Then we have other ones on closer to in the same orbits as Phobos and Deimos, or put them or something on those moons if we can, but near them that just shoot charged particles to, like, basically to the other side of the satellites.
Yeah.
In a similar fashion.
Yeah.
Increase the space of those magnets was kind of the idea.
Yeah, I think that we all sort of discovered that if Mars is ever going to be habitable, yeah, it might be 1,000 years from now, but that's a cool project. I'm down to like spend some tax dollars on it personally. If we're going to ever be on Mars, we got to get a magnetic field up. It's just going to be too much of a nightmare. If we rebuild the atmosphere, it's not going to stick around because the solar wind's going to rip it off. But I think we should. I think that people probably are thinking about this process with Io and the way that it's modulating the magnetic field. I think that's one of the more interesting things about this moon. And actually, it's quite fascinating. I guess you guys probably got more depth on your in the textbook from it, but I want to make sure that we have time to talk about. Here's a couple more pictures of it. This is actually just like a year apart, these pictures. So you can see that the volcanism is really changing kind of on the day to day. Is that a year apart? It might even be less. No, it's from November of 99 to February of 2000. So a few months actually difference. And all this volcanism, the idea is that since the thing is so close to Jupiter and it's being whipped around, that all that sloshing is really what's contributing to the volcanism and all of its internal heating and this thing being just kind of so active and crazy. Here's a picture actually of you can see one of the volcanoes off-gassing out into the orbit there, which is pretty wild.
That big.
What's up?
It's crazy how far it shoots.
I know, it's totally insane. let's see, Europa. Europa is an interesting one. I'm not going to dwell too long on these, but I do want to point out that this is kind of the first planet or first moon that might be attractive to us as a place to maybe set up a base at some point, depending on what we find. There's a comparison of it with respect to our own moon, so it's, on the order of our own moon. Yeah.
Isn't Europa the one that's theorized to have like large underground like seas, wait, oceans?
Yeah,
Just a
we don't know for sure, but I think that we'll find out soon. Um, so when we look at the surface of it, it appears to be kind of this dirty ice cracked thing. And if we do these sort of density estimates, it doesn't have much of a magnetic field. So people are thinking that it's not super metallic inside in the same way. But there's something about the way that, and I'm not capable of getting into the depths of this right now, but the way that the ice has cracked has led people to believe that there's liquid underneath it, essentially. It's sort of a materials science approach to what could be. Now, there's other moons that we're going to look at where they literally see geysers coming out of them, and they can spectroscopically tell you what sort of liquid is in that geyser. So we know this is a thing that happens. The hope is that perhaps Europa is one of these places that does that. And again, this is kind of what it would look like if it was the case. It's got a pretty small iron core, mostly silicate rocky mantle, and then this subsurface ocean, which could be rather enormous actually at the end of the day. It could be an icy ocean is one possible idea. It could be completely liquidous. There were some images. This is some like highly enhanced images from the Hubble Space Telescope that might point to some geyser activity, but I think that people are gonna want to get back there before they actually confirm this. If it is the case, the plan next would be to essentially take something like a nuclear-powered toaster and put it on the ice and let it kind of melt its way down into the subsurface area and study it that way. So instead of trying to drill your way through this ice, basically just melt your way underneath and see what you find. All right, so if we keep going, Ganymede's out there. Ganymede's kind of interesting.
so sparkly.
Yeah, it's really, really smooth and shiny. That's true. It's the only moon in the solar system that has an appreciable magnetic field, which is really weird. In fact, like the diversity, again, everywhere we go in the solar system, I just want you to like take note of how crazy different things are, even though they're collected together. It's very, very perplexing and strange. Given a uniformitarian formation history for all of these. So this one is very strange again, mainly because of its magnetic field. There it is in comparison to our moon, which you can see it's actually quite enormous. Let's see, it's actually the 9th largest object in the solar system. So it's quite enormous. It's by far the biggest moon in not by far, but it's the biggest moon in the solar system. Titan's going to be the runner-up, which we'll get to in a second. If we keep going, I'm not going to dwell on Ganymede, but it's pretty cool. There's ideas about terraforming it and all sorts of crazy stuff we can't get into. This one comes next. This one's completely insane for a different reason. Look at it. It's the most cratered object in the solar system, which is it's so beat, actually. It has by a long margin the most craters of any object in the solar system, which is super bizarre too on top of it. Again, these moons are relatively close by one another in orbit. They are all wildly different looking from each other in composition and appearance.
So like to Jupiter. So the same thing with like Mercury we brought up, if things go toward the sun, they generally fall toward the sun. So how could Callisto be as cratered as it is, the most cratered in our solar system, as close as it is to Jupiter?
I mean, I'm sure. I believe. Yeah, we don't have to get into it. There's a Just So story during the impact. You can come up with these kind of heavy bombardment type events that might be able to do it. It might just be incredibly, incredibly old and metamorphosized. From where I'm sitting, if you start with the presupposition, or if you start with the recognition that in the 1960s the universe was supposed to only be, I don't know off the top of my head, but somewhere on the order of a few billion years old. By the 1990s, the universe was, let's say, 10 billion years old. By now, the universe is supposed to be 14 billion years old, a little bit less. Basically, every time you build a new telescope, you see further, and the universe has to get older because you're seeing further in time back. You know, if you give me 200 billion years, I could make an object like this just by a natural sort of evolution of something that looked a lot more like an actual Jupiter at one point in time or something, right? So it's kind of two ways to bake a cake in some sense.
Would you still be able to do that in the uniformitarian model?
I think I could if I had 200 billion years or something. Yeah. The problem is that if you're trying to make this thing happen in 4 billion years, which is the limit that we've put on our solar system in the
Right.
Laplacian Kantian paradigm, it's very, very difficult to do that without some crazy events. It has to have had a bad day where it got hit with most of these asteroids. But yeah, maybe, I mean, in all reality, there's probably a lot of step function bad days, and perhaps the timelines are wildly longer than the standard approach has allowed for. And we'll talk about why they think those timelines too, beyond just cosmology. We'll get into that on the last day. But it has to do with the way that dating is applied and how dating actually works when it comes to rocks. But anyways, this thing's crazy looking. It looks super old to me. If I was just eyeballing these things in a pawn shop based on how old they are, I would say that's an antique right there. But who knows? The mysteries are deeper than the certainties that we can pin on them. And that's just the reality of studying the deep past, in all honesty. I'm not going to talk about Callisto. We did briefly mention Callisto. Jupiter has these huge swarms of asteroids that hang out. And it's like, what did I do?
The names, I just forgot they called them the Greeks.
Oh, the Greeks and the Trojans, yeah.
Jeez.
So these hang out in two of their Lagrange points, so it's kind of being tugged around by Jupiter in its orbit. This is important. I wanted to show you guys because this is, in some sense, why we're not getting pummeled by life-ending asteroids more often. Because Jupiter does a great job of scooping them all up for us. It's a really, really, really big planet. Again, I've compared it already to the size of stars. It's huge. It really makes up, other than the sun, it makes up the vast majority of the rest of the mass in the solar system. It's an enormous, enormous planet. So it holds on to asteroids for us, which is very nice. Now, let's talk about Saturn. Saturn's the next one out. Very similar interior floor plan. Yeah.
The last thing about Jupiter, if you go back to the orbit,
Yeah.
Something that shows just how strong and massive Jupiter is that it pulls the sun in a little.
Oh, that's true. Yeah.
The sun does a little, which is kind of a very weak version of like a binary orbit.
Yeah. I think that's a good way to think about it. Yeah. So what Dante is saying is that the Jupiter doesn't just orbit the sun orbits Jupiter to the extent that the center of mass between the two of them is, all right? The center of mass between Jupiter and the sun is actually outside of the sun a little bit. I think it's maybe like 10 kilometers outside of the sun.
It's not that big, but
it's not that far. But it is appreciable, yeah, which is pretty wild. So they are almost a binary system in that sense, which, just to throw some hand grenades in the room, I'm not going to say every, the vast majority of stars that we witness, that we are able to see, have partner stars, and it's really weird that we don't have one. We used to kind of started off thinking that the ones that had partners were the sort of exceptions, but we're starting to realize that our solar system's super weird because it doesn't have any other stars that it orbits. That's really, really strange. So, from this, from like a metamorphic trajectory, maybe we did have one in the past. Maybe it's even still with us, That's an interesting thought. So Saturn is really not so different. I don't think that we would think of it too much different if it didn't have these beautiful rings around it. The rings are a bit of a mystery. I think that people, I think that probably the most popular idea is that they're a busted up moon, which I think is not a bad idea. The reality is that if you look in different bandwidths, you'll actually see that Jupiter also has dust rings as well. They're just not quite as as visible. But as a planet, it's actually not so different.
Set rings.
I think they do, actually, now that you mention it. Yeah, I think it's a very common thing. It's actually not so different from Jupiter as you might think. Its moon systems are also super diverse and chaotic and orbiting in different directions and different collections. Um, you know, the sort of stories that are necessary to make this happen are very, very interesting and bizarre as well. But you can imagine that you basically need several different stepwise events to be able to pull together different swarms of moons. Saturn's another one. You can see it actually tonight if you really want to. You can see it. You won't be able to see its rings. I think that it's going to be a while before we can see its rings. It's turned on its side perfectly. So if you think about Saturn, let's see. Let's pull up a picture. This is a picture. It's kind of granulated because it's actually from a telescope, like an amateur telescope. But if it's depending on where it is as it's on its tilted rotation around the sun, it takes, let's see, about 30 years for it to go around the sun. So as its tilt goes into this perfect plane with us, all we see is a regular old planet, and that's unfortunately what you'll get if you go look at it tonight. But it is pretty cool, and you'll be able to see its rings again soon. So what else do we want to say about this? The rings actually have little moonlets in them, which is quite interesting. And they give them names. I'll show you a close-up of those in a second. There's also a super ring structure. So that little dot right there is actually Saturn. And there's this huge, what do they call this thing? The Phoebe ring, which is an even bigger ring system, which is actually offset from the main Saturn ring system. So Saturn has its ring, which is in its rotational equator, which makes sense, sort of rotates in the same plane as the planet itself. But then it has all these moons that are in different planes, and then it has a whole other ring system that's in a completely different plane. So whatever's been going on with Saturn, it has been varied, and I think there are a lot of different phases of the evolution of Saturn that we're missing out on because they've just been lost to time.
Was that photo infrared?
Yes.
And if you go back,
Yeah.
If you look at a little Saturn, it kind of looks like the sun.
Yeah. It's really remarkable. It's really remarkable if you start to see the similarities between the sort of crumbling line between planets and stars. A whole new sea of possible stories starts to appear before you. It's really interesting. Not much to say about the rings. I mean, hypothetically, they're leftovers from a moon or a pair of moons that collided, perhaps. They're extremely beautiful, and we've flown some missions out there in recent times to get close-ups of these. I'm trying to find a really good picture of this. Oh, these are one of my favorites. So, as this little moonlet kind of tumbles through the rings, it makes these very beautiful resonant patterns in some of the rings. This is they give these things names, of course. This moon is called Daphnis, and it's cutting this beautiful little scalloped structure called the Keeler Gap. And then you can see it over here as it's kind of like ripping its way through the rings. Not much to say, but it is quite beautiful. So let's close down. Last thing I want to point to is two really bizarre moons. Saturn has a bunch of different moons. Only 13 of them have diameters greater than 50 kilometers. And one of them is enormous. It's called Titan. It's our runner-up for the largest moon in the solar system. Super weird moon.
Titan.
What's that?
No wonder we called it Titan.
Yeah, it's big. It's Titan, right? Like the giants from what was this? I guess that's Greek mythology as well. Yeah. Now, almost all of this is a mass representation. Titan basically has all of the mass of all of Saturn's moons. It's quite enormous. And the one thing that I'll point out, since we only got 5 minutes left, about Titan, there it is compared to our moon. It has this really, really bizarre surface architecture, right? This very, very strange ammonia atmosphere. And some of the recent spacecraft that have gone out there have found that it actually has these liquid like lakes on its surface. But the lakes aren't made out of water like here on Earth. They're made out of methane, which is really crazy. And I don't think anyone expected that. Furthermore, what was really funny was that when I was a kid, everybody talked about methane and petroleum and things like this. They always called them fossil fuels, right? You guys probably I'm too young for this.
No,
They just stopped doing that one day, and I think it had a lot to do with the discoveries that they were making about Titan. And
I'm hearing them referred to as fossil fuels and dead dinosaurs all the time.
yeah. Well, that story doesn't check out, obviously, because nobody is thinking that there's a bunch of dead dinosaurs on Titan, right? But it's got a tremendous amount of fuel by way of methanes and so forth, to the extent that there's literal lakes of this stuff, which are quite beautiful. And then the last one that I want to leave you guys with, I know this has been a complete tour de force, but I think it's important to point out to you guys, is there's one other moon that's really fun out closer to Saturn than Titan. Titan's the furthest away of the big ones. This is Enceladus. Enceladus is a pretty tiny little guy, but we've gotten some incredible pictures and some great spectroscopy of these geysers on Enceladus, right? So everyone's pretty well convinced that there's a subsurface ocean on this thing, and everybody's super excited that it might have something living in it. And here's how, it's a tiny little thing, by the way. I don't think it's going to be a great place to hang out. It probably has almost no gravity. But this is why they're excited. They're excited because when they examine what's flying out of these cracks in Enceladus, they kind of find all the stuff that we might hope for if we were looking for critters. Water vapor, methane, simple organic molecules, carbon monoxide, complex organic molecules, and carbon dioxide, which is usually a respiratory product, right? So it has a lot of the little tantalizing pieces of the puzzle that we haven't seen in such proportions anywhere else in the solar system. And in some sense, I think it's our best hope for finding other critters out there. You got a question? Oh, you're just stretching. So I think what we'll do next week is we'll actually talk about the search for life before we swoop through the last group, which is going to be the Neptunes and we'll call them Neptunes in general. And then we'll close it down on trying to compare some different stories for how this whole thing happened in the first place. But we're getting really close, guys. Only 3 more classes. Everybody's going to be here on Tuesday. I'm going to invite my wife to help me give that lecture, so don't let me down. It's going to be embarrassing if nobody comes. But yeah, have a great weekend. And you got a question?
Mass in Daltons? What's a Dalton?
A Dalton's an atomic mass unit that nobody uses except for the chemists. Yeah, sorry. Good question. But yeah, have a great weekend, guys, and see you on Tuesday.
Like how the only reason